Hi, my name is Jeroen and I'm here today to talk about organ transplantation and individual treatment effects. Organ transplantation is a hard problem. Given the goal of assigning an available organ to a patient on the wait list, we wish to maximize the total population life years. This sounds very straightforward, however, it's not. So why is this such a hard problem? First of all, organs are unique and high dimensional. We only see the same organ once, in contrast to other ITE settings where we, for instance, want to assign chemotherapy or radiotherapy to a cancer patient. There is plenty of chemotherapy, but this is not the case for organs. Choosing a patient on the waitlist also means not choosing other patients on the waitlist. Some patients are sicker than other patients, so we have to define a good way of prioritizing patients on the waitlist. And there's a long-term effect for every patient involved, not only those that receive the organ, but the patients that remain on the waitlist. So we can take many perspectives to optimality in an organ transplantation setting. First of all, we can take a population's perspective, saying that optimality is more net life years gained throughout the organ transplantation process. We could also take an individual patient's perspective, saying that whenever we receive an organ, we wanted to maximize our life years individually. There are other perspectives like what does it cost to transplant an organ? We want to minimize organ waste. We want to maximize the ease of surgery, etc. However, each perspective implies some sort of compromise. From the population's perspective, perhaps the available organ should go to someone who needs it most rather than the best match. This is of course in contrast for the patient, whereby we want to receive the best organ that is optimal for me. We take a population's perspective in our work on individual treatment effects and organ transplantation. For instance, we optimize a population-wide objective that is agreed upon by the Liver Advisory Group by the NHS. We optimize for the total net life years gained as a population. That means we want to optimize life years on the waitlist as well as after the waitlist. Some considerations in this is perhaps it's best to give the available organ to a less suitable patient because they need it most. We have built a figure for this on the right. So say we can define organ similarity by the middlemost axis, whereby 2 points appearing close by each other are very similar organs. For patients on the waitlist, we have a density of required organs, and for the organs that become available, we have a density for those that are observed in the data. These densities might not align. So at the bottom, we have the density that represents the optimal organs for patients on the waitlist, whereas the above axis represents the density of organs that become available. If we have 2 patients that are indicated by these X's on the bottommost axes, we see that the optimal organ for these patients are not very similar. If we look at the organ that becomes available, we see that it's probably the best match to give it to the leftmost patient. However, because the rightmost patient actually requires a fairly rare organ indicated by the density below, it might be best to actually give it to the rightmost patient because they would wait too long and potentially die on the waitlist. Furthermore, an additional consideration is if we give organs to only the very sickest, this will likely result in less deaths on the waitlist, but also less added life years, because transplanting an organ does not perform miracles. So how does this relate at all to individual treatment effects? We can consider an organ transplantation to yield a potential outcome, indicated by the amount of life years the patient has gained. So for each patient and each organ, we associate a different outcome, that is Y of O, which indicates potential outcome, given X, the patient. Using standard individual treatment effects notation, we could write this as an expectation, whereby we want to estimate the expectation of receiving the organ, the potential outcome of O, minus the potential outcome given no organ, conditioned on X. Of course, this has many dimensions, whereby the potential outcome is indicated actually by a treatment that is unique and high dimensional. Same for X. So we will have to estimate this value because observing it is impossible. We cannot only observe transplant or no transplant, but because there are so many different types of organs, we cannot observe either transplantation for all these types of organs. We will then use this estimate to allocate organs more efficiently. Given that definition, in many ways, individual treatment effects in organ transplantation is standard. So the data is biased due to previous allocation, as we have allocated organs to patients in the past. The problem is easily written in terms of potential outcomes. We have a Y of O. There's a clear treatment, being the organ. There's a clear outcome, being the life years gained. And there's an individual, being the patient. However, in many other ways, it is not standard at all. First of all, the treatment, being the organ, is high dimensional and unique, so this would be a first. We only see an organ once. Organs are not pills. We have some of them, but they're scarce. The bias is also non-standard, as the patients to give an organ to is limited in the wait list. So while there are many possible patients, we only can assign the treatment to, let's say, 500 on the wait list. And ideally, there is no control group because receiving no organ implies death. We already know what would happen to a patient when they don't receive a transplant, otherwise they wouldn't have joined the wait list. So how should we go about estimating the individual treatment effect using OrganITE, a paper that we've presented at NeurIPS 2020? First of all, we need to reduce the space of possible organs. And we do this simply by learning K clusters using K means on the organ space O. So we have defined a function C of O, which will return one of K clusters given the organ. In this way, we reduce the organ space to a categorical variable, which we can use to estimate a propensity later. Second, we then use these clusters and the outcomes to learn a representation phi. This representation should be balanced through learning, first of all, the propensity of the organ cluster given this representation, which we learn adversarially. And second of all, we learn the potential outcome y given the representation phi, which is a combination of x and O. So learning phi is actually fairly straightforward. First, we learn the representation by maximizing the propensity loss on the cluster, which we now estimate. And this is done through a gradient reversal layer, which flips the gradient and learns the potential outcome, the propensity adversarially. Meanwhile, the loss in outcome prediction is minimized. So phi should represent some sort of equilibrium between estimating the propensity adversarially and estimating the potential outcome. So how should we go about incorporating the ITE estimate into organ allocation? Well, first of all, ITE in organ allocation is very important because the data is super biased by multiple sources. Some sources are the past assignment policies, which we've discussed previously, but also the clinicians themselves by accepting or rejecting offers of the assignment policies, and by the availability of organs and patients. So the patients are constantly changing because the wait list is, and the organs are unique, so we only see an organ once. We argue that you should combine three different components. First is the ITE estimate to have unbiased or balanced estimates. The second is the match, that is how well an available organ would match patients on the waitlist. And the third is rarity. We do this by considering the patient features, which here range from purple to blue to orange, but also the months that are left for the patient without an organ. In this case, the first patient would have 4 months left, and the available organ and what it would have on potential outcomes given these patients on the waitlist. So for the first patient who had 4 months left to live, we would say the available organ has an additional 6. This is because the features of the organ best match the features of the patient, both being purple. So the future organs in this setting are unknown. This is an additional source of the transplant system that OrganITE should consider. On the left, we see the incremental survival and best match policies would pick the first patient on the waitlist given the available organ. Sickest person first would pick the green patient because they have only 1 month left to live, while OrganITE would pick the blue patient at the bottom. This is because OrganITE combines the months left to live without an organ, that's very low, it's 2, The gain is 4, which is considerably well, and they need a fairly rare organ because blue is only captured once in the figure on the right. We estimate this density. So now that we know which elements OrganITE is combining, being match, rarity, and ITE, we see now how we actually do it. In principle, OrganITE composes a ranking of patients based on a score. And this score is a simple multiplication of these elements. Given the patients on the waitlist, so let's say it's 500, we pick a patient on this waitlist which maximizes this multiplication. The multiplication being the match raised to a negative exponent, whereby match is expressed, for instance, as a Euclidean distance between the optimal organ of a patient and the available one. Whenever the distance is very low, the negative exponent will increase this value, and the match will then have a bigger contribution to whatever score we come up with. We multiply this by the probability of the optimal organ of the patient on the waitlist. This too we raise to a negative exponent b, because whenever the rarity is high, so the value of the probability of seeing this observed organ is very low, we increase it by raising it to this negative exponent. These two are then multiplied with the ITE of the available organ given the patient of interest. So whenever this score is very high, we say, okay, this organ should go to the patient on the waitlist. To recap, the match is how alike the available organ is to the patient's hypothetical best organ. The rarity is how rare the patient's optimal organ is. And the ITE is what is the causal effect of the available organ. When this combination is high, we say it's a good match according to OrganITE. So we've tested this on given multiple different allocation policies. The first one is FIFO, which is a very naive first in, first out method of allocating organs. The second is sickest person first, which, as the name suggests, we pick only the sickest person on the waitlist. Then there's best match. This is a policy that allocates the organ to the patient that is estimated to have the highest potential outcome. A similar policy to this is currently in use in the United States. And incremental survival, which is the difference between receiving no organ and an organ. So basically the ITE, which is currently in use in the UK. And then confident match, which is a prediction method. So confident match is a variant of best match, but given different prediction methods. And then OrganITE. We have tested this on synthetic and real data. Both come with certain caveats, synthetic being that it is synthetic, and real data because we don't have access to counterfactuals in the real data, so we use different potential outcome models to estimate the counterfactuals. Given these simulations, we see that OrganITE has the best performance, and we attribute this to all three factors that OrganITE takes into consideration. I would like to thank you to have a look at organ transplantation in individual treatment effects estimation. It is a fantastic problem, and if you're interested, I highly recommend reading our paper on the subject. Thank you very much.